Continuity, Part 3. Let's look at a real-world-ish problem. So let's say that the position of a particle is defined by the function f of x is equal to sine of x plus 3, where x is the time and f of x is the position. We want to know what time the particle's position was 0. So that means we're looking where f of x is 0. So f of x is equal to sine of x plus 3 is equal to 0. And if we were to solve this equation for x, we'd know what time this occurred. Trouble is, we cannot solve this equation. At least not at this point. So what on earth do we do? Well, first off, we have to ask ourselves, does a solution to that equation even exist? And if it does exist, if we can't solve it, can we at least figure out where it kind of is? Like, what's a different interval of values where we might be able to find that solution? So let's just look at this graph real quick. So we're looking for where f of x is equal to 0. So that means we're trying to find the x-intercept of this function. And that is about right here. Whatever this value is, we can't quite be sure. So this is where f of x is equal to 0, whatever this x value is. And that's not quite good enough. So let's see if we can find some sort of nice-ish points on this function. So we have about here and about here, and it seems like when 0, so when f of x is between 1 and negative 2, we can look at our function and find some sort of input anywhere on this function that will give us that output. Whoop, that's the wrong way. Because our function is continuous. So no matter what output I'm looking at, I can find some sort of input. So that means that if I'm between 1 and 5, I'm hitting within this band from negative 2 to 1, which means at some point on this interval from negative 2 to 5, I'm going to hit this f of x is equal to 0. I don't know which x it is on that interval, but somewhere in that interval I'm going to hit it. And if I wanted to, I could get even closer to that. So I could look at, let's see, well, if I trap this f of x is equal to 0 between these two bands, then it seems like I can trap my x values between these two bands. So maybe this solution is actually between, this is about 1.5 to 4.5. So looking at this graph, I can try to get closer and closer and closer. And because this is continuous, I know that if my x values are between these red bars, my y values, or f of x values, will be between these blue bars. And because this 0 is between these blue bars, at some point on there, I'm going to have to hit whatever this solution is, even though I'm not sure what the x value is, I know where it might be, and I know it has to exist. So sometimes we can show that a solution exists and about where it might be, even when we cannot find the exact solution. And when we're just trying to show this existence and, like aboutance, like where about might it be, we use something called the intermediate value theorem. So the intermediate value theorem is, suppose that f is continuous on the closed interval a to b, and let n be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the open interval a to b, such that f of c is equal to n. So we're showing that there exists a solution, where it might exist, and what it makes true. Now, if intermediate value theorem works, then we show three things. First of all, f of x has to be continuous. So here is a nice continuous function. Next up, n has to be between f of a and f of b. And f of a cannot be equal to f of b. And if these things are true, there's a number c in AB. So let's find our AB. Such that f of c is equal to n. And this is only true when you've met all of the criteria. So if it's continuous on that closed interval, if n is between the two outputs, and if the outputs are not equal to each other. And one of those key pieces is the continuity, because if we look at a function that is not continuous, well, we might be looking for some sort of n where that's not actually an output of the function. So there actually isn't a c that makes that true. Even if you have an f of a and an f of b, if you're not continuous, this isn't going to work. So we really, really need that continuity in order to use the intermediate value theorem. There are three main types of problems that we solve using the intermediate value theorem. So we want to show the existence of a zero over an interval, a solution to an equation, or a number. And remember, we're not trying to find the zero or the solution or the exact number a lot of the times. We're just trying to show that it exists. So for all of these, remember that f of x is equal to the n, and that's a known output. And x equals c is the input that you're trying to show exists. So we know the output, we don't know the input. And because of this process, there's a bit of guessing and checking involved in the intermediate value theorem. But basically, we need to show that these three hypotheses are true, so that f is continuous on a closed interval a to b, n is any number between f of a and f of b, and f of a does not equal f of b. And if we can show these three things, then we can make this conclusion that c exists and where it exists. Showing that f of x is equal to sine of x plus 3 equals 0 has a solution is kind of complicated. So let's start with a simpler example. Show that f of x equals 2 plus 4 cosine of 3x has a 0 over the interval from 0 to pi over 3. the first thing that we want to do, if we're trying to show the existence of a solution or of a zero, we need to state the intermediate value theorem. And you want to make sure that you're stating this correctly and completely. So suppose f is continuous on the closed interval AB, and let n be any number between f of a, my parenthesis, and f of b, where f of a does not equal f of b, then, well, I don't need that comma, there exists a number c in the open interval AB such that f of c is equal to n. And there's a couple reasons we state the intermediate value theorem every time we use it. First off, it's just common courtesy when you have a proof, or like this is more of a pseudo proof in math, that you state the theorems you're going to use. So some theorems like this, as you get higher in math, we stop stating simply because everyone knows them. These are pretty popular theorems. But since you're just beginning to use these theorems and state them, it's good practice for later in math, where just common courtesy, if you're using a theorem, make it so that the people that are reading your proofs know what you're trying to do. So it's kind of like a topic sentence. It doesn't have every bit of information, but it tells the reader where you're going. So make sure you're stating the intermediate value theorem. Okay, now we're trying to show the three hypotheses, the first of which is continuity. So you want to state and justify continuity. So we're just trying to say that this function is continuous and give like a brief explanation of why it's continuous. So f of x equals 2 plus 4 cosine of 3x is continuous. And sometimes we have to be a little more general about the interval. Sometimes it's over its domain, but because this problem has a specific interval we're looking in, that's the one that we'll state. So this is continuous on, and remember this has to be a closed interval, so from 0 to pi over 3, because, and then we can look at the different pieces of this function if they're being added together. So because it is the composition of a constant and cosine function, which are continuous over their domains. So the types of functions that you'll look at for intermediate value theorem in like Calc 1 would be polynomial functions, cosine, sine, natural log, maybe an exponential function, maybe a square root function, but functions where we know, just because we're familiar with these functions, where they're continuous. So you probably wouldn't have to look at a rational function for intermediate value theorem. And if you did, you just have to make sure that whatever interval you had didn't include its discontinuity. So we've stated that we're continuous, and that's the first piece of our hypothesis for the intermediate value theorem. Next up, we need an f of a and f of b. So we need to find f of a and f of b. If you're not given an interval, this is going to involve a lot of guess and check. If you are given an interval, this isn't too bad, because we'll just need to check the ends of our interval. Those will be our a's and b's. So we need to find f of 0, so that's equal to 2 plus 4 cosine of 3 times 0. So that's 2 plus 4 cosine of 0, which is 4 times 1, which gives us 6. And we need to find f of pi over 3, which is equal to 2 plus 4 cosine of 3 times pi over 3. So that's 2 plus 4 times cosine of 1. Sorry, cosine of 1 pi. So that's 4 plus negative 4, which is equal to negative 2. So I found my f of a and my f of b. So f of 0 is equal to 6, and f of pi over 3 is equal to negative 2. Now we need to state our conclusion. In order to state the conclusion, we're going to actually have to think about what we wanted here. So we're trying to show that this has a 0. The 0 of a function occurs where f of x is equal to 0. Remember that the f of x, whatever it's equal to, is the output that is your n. So the output that we're trying to find an input for. The 0 will be whatever x causes this to be true. So rather, this is at f of x is equal to 0. So whatever x will cause this to be true. So let's see. So since f of x is continuous, on the open interval from 0 to pi over 3, which was our first hypothesis, and we found our f of 0 and f of pi over 3, and they're not equal to each other. So f of 0 does not equal f of pi over 3. And 0 is between f of 0 and f of pi over 3. So those are the three pieces of the hypothesis that we need in order to make our conclusion, which is there must exist a number c in 0 to pi over 3 such that f of c is equal to 0. So now we can make our conclusion about the existence of our zero. So thus, f of x equals 2 plus 4 cosine of 3x has a zero over the interval (0 to pi over 3) by the intermediate value theorem. So we showed the existence of our zero using the intermediate value theorem.